Hi, my name is Corey Cianello, and this is Physics 2212 Lab 1. In this lab, my goal was to find the magnitude of the charge on a piece of clear tape. I charged two strips of clear tape, the U-tape in the figure, by ripping them from another strip, the base tape, which was stuck on my desk. This quick removal charged both of the pieces. I then wanted to quantify this charge. I did so by loosely hanging one of the U-tapes between two stacks of books, and I brought up the other one until the hanging strip began to float like in the picture. I measured the distance between the tapes at which this occurred, and I used it to calculate the charge on tape B. When I handled the tape, I did so carefully by the ends as to minimize the amount of surface area that was in contact with my hands. If there was a large area touching, then more of the charge would dissipate into my body and the tape would be neutralized. In order to simplify calculations, I made a few key assumptions. First, the only forces that I accounted for were gravity on tape B and the electric forces between the two tapes. This means I ignored small forces like air resistance and the stickiness of the tape to the books. I also assumed that both had the same amount of charge and that the charges were evenly distributed. This is reasonable as both tapes were about the same length. Finally, I treated them as point charges, with all of the charge located at their centers. Both of my U-tapes were about 20 centimeters or 0.2 meters in length. Multiplying that by the given density of 1 gram per meter, I calculated the mass of one of the strips to be 0.2 grams, or 0.0002 kilograms. The distance between the two pieces when tape B floated was 2.5 centimeters, or 0.025 meters. I also found the tapes to be positively charged. I came to this conclusion from the plastic pen test. I rubbed a clear plastic pen in my hair, giving it a negative charge. I then held the pen close to the U-tapes, and they were both attracted to it. This must mean that they are positively charged and lost electrons to the base tape. It was now time to calculate the magnitude of the charge. First, I calculated the weight of one of the pieces of tape by using the mass from the previous slide. I found it to be 0.001962 newtons. The next equation is for the electric force of one piece of tape on another, assuming that the charges on both are the same. Since the gravitational and electric forces are the only forces acting on the system, and the system is in equilibrium, this must mean that the two are equal. Substituting the value of Fg into Fe, I find the charge of one of the tapes to be 1.1673 times 10 to the negative 8 coulombs. I divided this number by the charge of one electron, 1.6 times 10 to the negative 19 coulombs, to find the total number of electrons lost, which is 7.3 times 10 to the 10. I can analyze this number by comparing it to the total number of atoms in the tape, and I calculated the ratio to be 1 to 1.872 times 10 to the 7. This means for every one atom that lost an electron, there were many, many more that did not lose an electron. I also made a model in GlowScript where we can visualize the relevant forces. The green dot is the point charge representing tape B, and the red one is tape A. The green arrow is the electric force of tape B on tape A, and the red arrow is the opposite. The blue arrow is the force of gravity on tape B. As we can see, it is in the opposite direction and is equal in magnitude to the electric force of tape A on B. I have also restated the calculated values below. What if the charges of electrons and protons were switched? Then the tapes would still repel each other, as they would still both have the same sign, and my calculations would remain valid. However, they would have opposite interactions with other neutral and charged objects. They would now repel negatively charged bodies, for example. In conclusion, plastic tapes are positively charged, and by isolating the system and making some assumptions, and only measuring the separation distance, I could calculate the magnitude of the electric force. This is a very useful method of analysis that can be extended to other uniformly charged objects.